Yesterday, we left off talking about directional derivatives. I want to finish off that conversation today and hopefully get started on the next section from the textbook. Though it's jumping around a little bit. We're finishing up chapter 2. We had already started chapter 3 a little bit last week, but we want to finish it off not finish it off, but we want to jump back into chapter 3 this week. So we're going to finish off chapter 2 today and hopefully get started a little bit on the next section of chapter 3. So we've been talking about directional derivatives. I highlighted a couple things in this definition. First of all, when we take the derivative in a certain direction, we always want to make sure that the direction vector is a unit vector. It says normally here, but I said just err on the side of always. And then there's this fancy definition here, but realistically, we're always using this theorem for how to compute the directional derivative, which is just the dot product of the gradient with the direction in which you're taking the derivative. And so that's kind of how we'll take it. In my head, this is kind of, I keep this as the definition of directional derivative, even though technically it's this, but this is kind of how I think about it. Okay, cool. We did an example yesterday. We did this example. I want to go through another example. I promised some pictures and some demonstrations, so I want to get to that today. But first, I want to set it up with this sort of with this example here. So first of all, we're going to compute the derivative of this function at this point with this derivative in this direction. So the first thing we always do, right, is, if you remember from yesterday, is make sure that v is a unit vector. So make sure that v is a unit vector. Okay. And so we're going to just compute the norm of this guy, which if you see, so the norm, so we compute the norm of 1, 3. And we take the square root of 1 squared plus 3 squared, which is clearly not going to be 1, right? Because this is the square root of 10. And so that's not 1, but this helps us a little bit because then we can just let v equal 1, 3 divided by the norm of 1, 3. So that's going to be 1 over the square root of 10, comma 3 over the square root of 10. We just divide everything by the square root of 10. This norm we just got. Okay, so this is making sure that v is a unit vector. Okay, cool. Now, what can we do? Well, we can say, use that definition that I just showed you in this blue box right here. And we're just going to compute the gradient. So compute the gradient of this function. So the gradient of f. This is going to be equal to, we take the derivative with respect to x, so that's y plus y squared, okay? And then we're going to compute the derivative with respect to y, which is x plus 2xy, okay? Now we take that gradient and plug in -1, 1, which is the point where we're taking the derivative, where we're taking the directional derivative. Plug that in here. So plug this point -1, 1 into this. So -1 is x and 1 is y. So we get 1 plus 1 squared. So we get 2. And we get -1 plus 2 times -1 times 1. So -1 minus 2, which is going to be -3. Okay. And last but not least, we take the dot product of these two numbers. So we're going to take 2. Someone's asking, I guess before I move on, where did I get this y plus y squared? Yeah, I'm kind of speeding through this, but yeah, I'll totally take it. So here we took the derivative of this with respect to x. So the derivative of xy with respect to x is just the y. The derivative of y squared x with respect to x is just y squared. You can factor out the x if that makes it easier. So this is y plus y squared times x. And so that gives us, this is, you could think of that, all of this, the y, remember, doesn't change with respect to x. And so we can say that this is just like the coefficient on x. And so we treat it as such. Okay. And then we plugged it in here. So let's go ahead and compute the dot product. So the directional derivative that we're looking for is just going to be the norm, or not the norm, the dot product of 2 comma negative 3 with 1 over square root of 10 comma 3 over square root of 10. Right, this here is going to be the actual directional derivative. So our final answer is going to be 2 square root of 10 minus 9 square root of 10, right? Negative 3 times 3. This simplifies to negative 7 over the square root of 10. Okay, cool. So I kind of rushed through that, but let's kind of go over the broad strokes. First thing we did is we normalized the direction vector. So we started by normalizing the direction vector just to make sure that we're set up okay. Then we took the gradient of our function, right, which is where all the calculus comes in, right? That's when we do derivatives and stuff. Then we plug in the point we're given into that gradient. Now we have two vectors. We have the direction vector and this new gradient vector. And then we're going to take their dot product, and that's going to be our final answer. Cool. So someone's asking if I could explain when we normalize the vector. So I would say, so if we look back at that definition, it says we need to choose v to be a unit vector. So if you're not given a unit vector, then you just need to normalize it. Now, the process of checking whether something is a unit vector involves taking this norm here. And so if you just get 1 here, you can just always do this process, is what I'm trying to say. Always do this process. And if you already were given a unit vector, then you get 1 here and you just divide by 1, so it doesn't change the vector. But if it's not 1, then you've made sure that you end up with a unit vector. So always start by normalizing this vector. And if you happen to have a unit vector to start, like we did over here, you see that the norm was 1. And so if we had just normalized this, we would just divided everything by 1. And so we didn't change it. But in this one, we actually got something that wasn't equal to 1. Now, the reason for normalizing is because we want to make sure, remember that the derivative is computing like a rate of change. And so we want to make sure that right, so you can think of that as like a rise over run. And this unit length is making sure that our run is always equal to 1. Okay. By making that unit length, we're making sure that the denominator is always 1 on that rise over run thing. And so we're only the directional derivative is only giving us the rise. It gives us a sense of scale, basically. Make sure that whenever we compute the directional derivative, we're always using the same scale, if you will, like the same units almost. It's kind of how you can think about what this is, what this number is representing. It's representing the rate of change in that direction. So if we were standing on the graph of this guy and then we faced in this direction, the slope would be negative by this much. So speaking of which, negative by this much is actually pretty negative, right? Because square root of 10 is bigger than 3 but smaller than 4. So this number here is definitely going to be, it's going to probably be bigger than 1, maybe bigger than 2, depends on how, I'd have to compute this a little better to figure it out. But it's, it's going to be that's still pretty steep. It's a slope bigger than 1, but in the negative direction. And so it's downward sloping in that direction. And so I want to kind of highlight a little bit about what this represents geometrically. And so I want to draw a little picture, and then I want to also switch to GeoGebra at some point. So you have your coordinate plane. Okay. And we're at the point -1, 1. So we're right here. This is -1, 1. Okay. And this is our domain. This is the domain of the function, right? F goes from R2 to R. So the domain is R2. So we're over here living in the domain, and we're saying, I want to go in I want to go to the right 1 and up 1, 2, 3. So I want to head in this direction, but I don't want to head in this direction all the way. I don't want to head like, according to that vector that's given, you would think, oh, we're going to head in this direction, right? Now, that's fair. We do want to head in that direction, but this vector's too long because remember, it's all about normalizing and making sure that the rise over run, the run is always just equal to 1, right? And so we want to make sure we shorten this into just a little vector. It just pointed in that direction, okay? Okay. So now I'm going to switch to GeoGebra to kind of show you what this all means, okay? In terms, in a little more geometrically, so that we can all kind of be on the same page. So let me go ahead and do that. There we go. Okay, so you can see here on GeoGebra in front of us, this is the graph I just drew, right? This is the graph I just drew, right? You have your XY plane, and then you have the point -1, 1, and it's kind of pointing in that direction. So what we can do with this is we can say, okay, so that's, let's see, let me make sure I know what I'm doing. Here. We can basically create a line that kind of runs along that direction. So this line kind of is saying, if we just moved in this direction, this line would represent kind of what happens if we move in that direction, right? Okay. Well, then what we can do is we can say, okay, now let's put this into the context of the graph of this function xy equals x squared y. So here I've graphed it. And so let me give it a little spin. And so it's probably a little fast. So you can see here that we have the graph of this function, and this line, this gray line, is kind of saying, okay, this is what happens if we just move in that direction starting at that point, right? And we get this graph here. And what we can do is we can say, what happens if we plot that whole graph along this surface, right? Along the graph of this. If we just focus on the part of the graph that comes from this line, right? Then we get this sort of this blue function here, okay? And now what I'm going to do is I'm actually going to, let's see, wait a little bit and then stop this from spinning. Okay, there's good. And then I'm going to make this invisible, and we can see, okay, now we can just focus on the part of that graph that comes from this line. And if I move to the right angle, this now looks like a function in one variable. We can treat that gray line that is now just kind of been absorbed with all the axes, and the numbers got all janky because it's at a weird angle, but we can kind of ignore the numbers. We can just treat that line as if it was the x-axis from normal single variable calculus. Then we can kind of do we could kind of look at, okay, so this point becomes this point, and we can see, what is this? Oh, no. Then we can see that this vector, going in this direction gives us a downward slope here. Okay. And that it's a pretty steep slope here. So this here is what the number -7 over square root of 10 represents. It represents the slope. If we just focused on this graph that we're looking at, imagined that this gray line was the x-axis, and the vector is telling us which direction is positive, right? That vector is telling us which direction is positive, so you don't accidentally look at it from the wrong side, right? Because you could look at it this way too. And then it looks like the direction, like it's increased, like the function is increasing at that point, but we need to make sure that that vector is pointing to the right. Okay. Okay. And then now it's clear that, oh, the function is decreasing in that direction. Okay. Because if we just did that, brought everything, the whole picture back, then you can kind of see, oh, if we kind of move in that direction, it's clear that this function is decreasing. So that's why we get a negative number for a directional derivative, and it's pretty steep, which is why we get, -7 over square root of 10, which I mentioned is about 2. It's close-ish to 2. Okay. Cool. Any questions on that? Does this picturing this graph help out a little bit? Okay. kind of getting this. I strongly encourage you to do stuff like this. I know if you're looking at this, this might look kind of complicated because there's a lot going on, but so it takes a while to get used to GeoGebra. So that's why I'm doing a few examples for you. But you can see here that this is kind of what I'm imagining when I take a directional derivative. You draw a line in that direction, and then you kind of plot it on your graph on the surface. And then you just get this single variable calculus problem, and it's clear that, like, okay, now we just move, bloop, we just kind of do that. Cool. Any questions? Let me switch back to my notes here. Okay. Hopefully that little that picture, the 3D graph helped a little bit. Okay. Cool. And if you have questions, feel free to slow me down. Okay. Cool. So that's this problem. Hopefully you that helped. Next, we're gonna go back and talk a little bit about the gradient, right? So we've been using the gradient in all of these problems. We want to talk a little bit more geometrically what the gradient is supposed to represent. So there's a couple of theorems from the textbook. I've given the page numbers here if you want to read them in full. If you've seen, as you may have noticed, the textbooks tends to explain things in full detail and with full, kind of everything kind of taken care of. But that can be kind of, it can get kind of confusing. It can be kind of hard to see like which parts to focus on. So I've given you the page numbers here so you could reference them. But just kind of the gist of everything is, the gradient geometrically of a function, right, is points in the direction of greatest increase of f. So basically f of x, f is a function, right? So maybe I should say that here, f is a function from Rn, and then since we're talking about gradients, this should be scalar valued, right? So in the vector, the gradient of f will be a vector, and that vector will live in Rn, and it's basically saying at a point, if I plug in a specific point, the vector is giving me a certain direction, and if I go in that direction, that's the greatest rate of increase I could possibly take for f. And now that we know what a directional derivative, we know what that means, right? So basically, if you take the directional derivative in the gradient of f direction, that's the biggest it can get, right? And it kind of makes sense because of the way we to compute the gradient is we take the gradient and we dot product with the vector, the direction, right? And so the gradient dot product itself is going to be kind of the biggest you can get by taking the dot product of the gradient with itself. There's a problem on the homework that kind of walks you through the process of why this is true, why this ends up being true, based on our kind of dot product definition of directional derivative. Okay. Okay. And the second theorem here is already kind of given in full here. So the gradient is normal to level sets. That's kind of the full thing. The book does kind of give this other explanation, and maybe I'll kind of summarize that explanation here. So if S is a level set at of f, right? What does that mean? That means that S is the set of all points such that f of x is has a specific value, a certain fixed value, right? And C is a path which lives in S, then the the gradient of f dot with c prime is equal to, actually, I should maybe say a little more. The gradient of f at c of a certain point, specifically we can say c of 0, is equal to c prime, or no, dot product with c prime at 0 is equal to 0. Okay. So, and you can and if you have a path, you can always reparameterize it so that 0 is a certain is in that path. But basically, what this is saying is, I'll draw a picture here. If you have kind of your level set, right? So we've seen if maybe in the n equals 2 case, the level sets are these curves living inside of f of x, y equals k, right? And if maybe you have a path that lives along this this level curve, let me draw a picture. Then let's say something like maybe this here is C. Then you pick a certain point along this path, and the derivative of this here is C prime at 0, and then the gradient is going to be orthogonal to this, right? Because the dot products are 0. That means that they're orthogonal. So this here is going to be the gradient of f at c of 0. Okay. And they're going to form this right angle right here. Okay. Any questions on this? So this gives like a more thorough explanation, but you can just think the gradient is normal to the level sets, right? So if I have a level set, maybe in R2, if the domain is R2, then you get a picture like this. If the domain is R3, then you're going to end up with this surface, right? The level sets are going to be these surfaces, and you pick a point, and then you get the normal vector at that point. Okay. Cool. It's the direction of greatest increase. That's the other kind of thing. And then we get a lot of cool word problems about that. And there's some stuff on the online homework that you can take a look at too, but we'll go through some basic examples here. Okay. So here it's asking us to find the direction of greatest increase at -1, 1 of the function f of x comma y is equal to this value right here. Cosine of pi x, sine of pi x. So in order to find the direction of greatest increase, we just saw in the slides that that's given by the gradient. So we're just going to compute the gradient of f. Switch colors. So the gradient of f is going to be equal to the derivative of this with respect. Oh, I made a typo when I wrote this problem down. One of these should be y. That should be a y. Sorry about that. Changing the problem on you. But let's take the derivative of this with respect to x. Well, this is negative pi sine of pi y, or sine of pi x, and then sine of pi y. Okay. And then we have pi cosine of pi x cosine of pi y. Okay. Okay, cool. Okay, so now we're going to plug in to find the direction of greatest increase at a specific point. We plug in that point, so -1, 1. And so we get negative pi sine of negative pi sine of pi. And then we get pi cosine of negative pi, cosine of pi. Okay, so now what is sine of pi or sine of negative pi? They're the same. And what value is that? Anyone know? Any takers? Sine of pi is, picture the graph. Zero, there you go. Yeah. So sine of pi is 0, right? And now cosine, oh, this should not be a comma here. Cosine of pi is different. So cosine of pi is, so again, we're gonna get the same value for both of these, but cosine of pi is, the graph starts at a different place. So cosine of pi is gonna be 1 or negative 1? Someone said 1, I think it's negative 1, right? Yeah. Cosine of 0 is negative 1, and cosine of 2 pi is, cosine of pi 0 and 2 pi are gonna be positive, but cosine of pi is gonna be negative. So this is gonna be negative 1, but then both of these are gonna be negative 1, so they end up canceling, and so we just get a pi. So this here is negative 1, and this is also gonna be negative 1. Cool. And so this here is our direction of greatest increase. Okay. Cool. So there's a couple of problems. I think there's one problem on the online homework, at least, where you can kind of think of this in 3 dimensions. So you can take a function in 3 dimensions, which is describing the temperature at a certain point. In, for example, like if you imagine a room is 3-dimensional, right? Because there's, you have 3 dimensions. So if you take the temperature at any given point in the room, that changes, in these 3 as a function of these 3 variables. So what you can do is you can say at a specific point, which direction do I have to go in order to make sure that for the temperature to increase, and you're just computing a gradient and plugging in that point, and that's going to give you that the direction to increase the temperature. Okay. And so that's kind of how you can do it. Cool. Let's see another example here. So let's find a unit vector normal to the surface given by this equation here. Okay. Now this isn't exactly like what we saw on a few slides ago on like the definitions. So we have to mix this up a little bit, right? Because in order to compute normal vectors, we need to be, according to this theorem here, we need a level set of some function, right? So what we're going to do with this is we're going to rewrite this equation so that all of the variables are on one side. So move variables to one side. Okay, so here we're going to say cosine of xy minus z is equal to 2. Okay, and then we're going to let g of xyz equal cosine of xy minus z. Okay, so what we've done is we've moved all the variables to one side and said that side of the equation, which has all the variables, we're just going to call that a function of xyz. Okay, so g of xyz is equal to everything there. And then basically what this surface that we're looking at, which is given by this equation, is just the level set of this. So the surface that we're looking for is the level set of g at, so we're basically this level, the surface is the level set g of xyz equals 2. Oh, I didn't give it. Oh, got to be more careful when I'm writing these problems. So there's a problem with this problem. we haven't encountered it yet, so maybe I'll wait until we encounter it. Or maybe I'll give you a chance to see if you can see what the problem with this problem is. But for now, we're fine. So far, what we can do, right, if we're computing the gradient, or sorry, the normal vector to a level set, we just need to compute the gradient, right? So we need to give you the gradient of g is equal to, so we compute the derivative with respect to x. So the derivative of this with respect to x is negative y sine of xy, right? So I'm taking the derivative of this with respect to x. You can ignore the z. You treat y as if it's a coefficient on x, and you move. So you take you do a chain rule here. Now, similar with when you take the derivative with respect to y, you get negative x sine of xy. And then when you take the derivative with respect to z, you just get a -1. Okay, cool. And now maybe you can see the problem with this problem that I wrote. What's the problem with this problem? Can anyone tell? If you're computing a normal vector on a surface, right? I can't just say compute the normal vector of this surface. I need to tell you where to compute the normal vector, right? Because if you have a surface, if you imagine the surface is kind of like this, the normal vector over here is going to point in this direction, but the normal vector over here is going to point in this direction. And so I need to also be giving you not just the surface, but I also need to be giving you the point. So maybe we'll say I'll come in and add, should have been part of the original problem. Come on, at, and now I just need to be careful to make sure that everything I include is going to, so 2 pi and -1. Okay. So this should have been part of the problem. It wasn't, but that was my bad from writing the problem. But imagine this was part of the problem. Because now we just take the point that we were just given, right? Now, this point lives on this, should satisfy this equation. But if you're given this information, you can assume that it satisfies that equation, and just kind of roll with it. Though whoever wrote the problem should check that. Like I hope I did correctly. But now you can just take this point that you were given, we had it the whole time, and plug it into the gradient here. So the gradient of g is at 2 comma pi comma -1. Now we plug all of this in, so we get negative pi sine of 2 pi, -2 sine of 2 pi, and then -1. And because there's trig stuff and we're plugging in pi's, we're going to see some both of these terms end up disappearing. So we just get 0, 0, -1. Okay. Cool. So now we should normalize this. So normalize, right, to make sure it's a unit vector. But in this case, right, that's going to give us the normal vector is going to be 0, 0, -1 divided by the square root of come on, the square root of 0 squared plus 0 squared plus -1 squared, which is just 1. So this was already a normal vector. Or yeah, sorry, this is already a unit vector in this case. But in general, it might not be. So that's why I want to include this step in case you're reading the notes later and you're like, I did all of this stuff and then I'm not getting the right answer. It's because you have to normalize it at the end. In this case, you just happen to get a unit vector off the bat. Okay, cool. Any questions on that? So again, my bad on writing the problem. I forgot to include this point where to take the normal vector, but on a well-written problem, that'll be included. Any questions so far? Okay. So I think I have a couple more pages. One last topic to cover, which is related. So basically, if we can see from this problem that we have a way of taking surfaces and finding the normal vector, right? If you have a normal vector, then you can find a plane, right? And so that plane is going to be the plane that's tangent to that surface. So let's see that here on the next slide. So if we have a surface in Rn, or in R3 specifically, and it's given by as the level set of a certain function. So basically, you can always take, if you have some equation that describes a surface, it's going to, if it's a surface in R3, then it's going to be some kind of equation with 3 variables. Move all of the variables to one side. That means that you're looking at a function of x equal to the level set of some function of x. And you want to find the plane tangent to that surface at a certain point. So you see here, I even told you, like, you got to find a certain point. Then we already saw how to compute the normal vector up here. And so we can just say that the gradient is normal to that at that point. So we can just use that in our good old-fashioned equation for a plane. So we take the dot product of the gradient of f at x naught, y naught, z naught, dot product with x minus x naught, y minus y naught, z minus z naught. And because this is, we want the tangent plane and we want it, that should be normal to the gradient, that's going to be, this should give us 0, right? So this should look familiar, right? This is going to be basic. We're going to treat this as our ABC, our capital ABC from that equation from before, right? So this, if we rewrite this, this becomes df dx at xyz, or x naught, y naught, z naught, times x minus x naught plus df dy at x naught, y naught, z naught. Oops. X naught, y naught, z naught times y minus y naught plus df dz at x naught, y naught, z naught times z minus z naught equals 0. Z naught, z sub 0. Okay, cool. And so this is kind of, this should look familiar, right? From our equation for a plane, this is going to be your A, this is going to be your B, and this is going to be your C, right? Because we remember the gradient gives you the normal vector. I keep just giving a thumbs up, but should be picturing kind of like a surface here, living normal to it. Okay, cool. Any questions? Okay. Okay, so we've got this nice fancy new equation for a tangent plane, a tangent to a surface in R3. So specific, the thing about this is that it's specifically for surfaces in R3, right? So we can use this and we can compute our tangent planes. So for example, we can see here, we're going to see this surface given by this equation, right? And we're going to find the tangent plane at this point here, okay? So this time, this problem, it was good, and I remembered to give you that point. So what we need is to set this up, right? So we want to say, okay, this is going to be our function g of x, y, z, or f of x. For some reason, I use g. And we're going to compute the gradient of this guy to get the normal vector, and then use that to find the tangent plane. And so we compute the gradient of g. That's going to be the derivative with respect to x of all of this. So that's y plus z, right? So these both have x's in them, and so you just, the x's go away and you get y and you get z. This one goes away completely. The derivative with respect to y, which is x plus z, and the derivative with respect to z, which is x plus y. Okay. Cool. Yeah, so hopefully if you I'll reiterate that. So the derivative with respect to x, this x goes away, so you just left with y. This y goes, this x goes away, so you just left with the z. And then over here, this whole term goes away. Okay, and you can do something similar happens for y and z. Okay, and now we want to, for our normal vector, we want to actually plug in 1, 1, 1 here. So 1 for all of these values. So this is actually pretty straightforward. When you plug in 1, 1, 1, you get 2 because you get 1 plus 1, and then 1 plus 1, and then 1 plus 1. So you just get straight 2s all the way across. Okay, so this is giving you your tangent vector. Now, on this problem up here, it asks specifically for a unit vector. Over here, it's not asked, we don't need a unit vector necessarily because we're not computing a directional derivative. We're just computing the equation for a tangent plane. And for computing the equation for a tangent plane, it's totally okay to not use a unit vector. And so here we're going to use this 2, 2, 2. And we're going to take the dot product of this with x minus 1, y minus 1, and z minus 1, right? So it's x minus x sub 0, y minus y sub 0, and z minus z sub 0. Okay, and we're going to set this equal to 0. Okay, we take this dot product, we get 2x minus 1 plus 2y minus 1 plus 2z minus 1 equals 0. Okay, simplify, this would be totally acceptable, but I'm going to go ahead and simplify. So you get 2x plus 2y plus 2z minus 6 equals 0, or you can move the negative 6 to the other side and you can just call this all equal to 6. Okay, and that there is our tangent plane. Cool. Any questions on that? Am I doing on time? Okay, cool. Okay. Okay, so that's this section. That's section 2.6. Remember we covered directional derivatives in this section, and we also talked about this geometry of gradients here. And so that's going to be the two big takeaways. Make sure you're keeping up with the homework on that because there's a lot of good examples there. And so if you're struggling with that, then those are good questions to ask in my office hours tomorrow. Okay, cool. So that, like I said, that's it for this section. And then that wraps up the chapter 2, right? So we've now made it all the way through chapter 2. And we started chapter 3 in the middle of chapter 2. We bounced ahead and did one section out of chapter 3. But now we're going to jump into chapter 3 in earnest and actually get some of the start one of the later sections. So we're going to jump to 3.2 today. So 3.2, which is all about Taylor's theorem. Oops. Taylor's theorem here. So we're going to talk about Taylor's theorem, which you may remember from like a single variable calculus class. Sometimes it's talked about in a single variable calculus class. Yeah, so we're going to talk about Taylor's theorem today. So let's start, before we get into like Taylor's theorem in earnest, Taylor's theorem is all about approximating smooth functions, differentiable functions. And so I want us to remember this situation that I had here, which was linear approximation of functions, specifically functions from R2 to R, right? What we did to approximate functions from R2, first of all, this approximately only works if x comma y is near x sub 0 comma y sub 0. And you may have already gone back, and if you've been looking at the homework, you may have done problems like this. I don't know if the TA went over one. I don't remember if I had a TA go over one of these problems yesterday, but if maybe you asked him about it, because I know people tend to struggle with that one, with those types of problems. So if you've been struggling with that type of approximation problem, then maybe you then you want to remember this formula here, and maybe I did an example of it in lecture last week too, but this was kind of the formula we used, right? And now this is starting to look a little bit more familiar, right? Remember, we just talked about the tangent plane, right? And that looked very similar to this part of the equation, right? And then this is a little different, but basically what we did to compute the linear, to compute an approximation of our function f of x is we took a point. So usually x sub 0, y sub 0 is a nice point. So usually, hopefully, with something having to do with integers, whole numbers that we could plug in. And then this point is maybe not a super nice point, but it's close to that nice point. Okay. And so we start by plugging in the nice point. And then we add in some error terms to kind of get close to it. And we do those by taking the partial derivatives. And then we multiply by how far. This is basically telling you how far the point this xy is from x naught, y naught. Okay, this here is telling you how far away that is. Okay. So I'm going to do a little bit of manipulation here. I'm going to give these some names. Okay, so I'm going to call this h1, and this is going to be h2. So x minus x naught is h1, and y minus y naught is going to be h2. Now, this is going to seem random, like why is he doing this? But I'm doing it for a couple of reasons. I'm doing it mostly just because this is kind of the notation we're going to use when we start talking about Taylor approximations. And this linear approximation is very much related to Taylor approximations. And so this is f of x, x naught plus y naught is h1 times the partial of f with respect to x at that point, plus h2 times the partial of f with respect to y at that point. Okay. So now instead of thinking of x and y, we're just thinking, okay, this is the distance from that point. This is just how far are we from x naught and how far are we from y naught. We're just kind of saying, okay, you're this far from x naught, you're this far from y naught. Just keeping track of the distance there. And on the right-hand side, on the left-hand side, we can rewrite x, right? If h1 is equal to x plus x minus x naught, then we can rewrite this, and you can verify this arithmetic here. X is just equal to x naught plus h1, and then y is just equal to y naught plus h2. Okay, and you can verify this basically if you take this and you add this, then the x naughts cancel and you just end up with x. Okay, but if you're thinking of this h1 and h2 as your distance from x naught and y naught, then of course this makes sense, right? X is just x naught plus the distance from x naught to y naught, right? And so you can kind of say, okay, this, if we want this point, we can just say, okay, I'm this far away from this point, add them together. This far away from this point, add them together. Okay. And so that's how we're getting this sort of formula. And so this looks a little wacky. It looks like, okay, why did I introduce these h's? But the point is that this tends to be the form we see when we talk about Taylor's theorem. And we'll see that here in just a second. Okay. But I just wanted to brush up on kind of the idea of linear approximation, kind of saying, okay, we have the basic term. We just take that point and plug it into the function. And then we say, okay, we look at these terms which have to do with the partial derivative and their distance, and they're multiplied by the distance from this point here. Okay. And it's important to know that this just tells us, so basically what this x, xy being near x naught, y naught is the same as saying h1 and h2 are close to, or I should say are small here, right? Because if x is close to x naught and y is close to y naught, then this number is going to be a small number, right? The difference between this is measuring the distance between the two numbers. And so if these points are near here, then these numbers are going to be very small. Okay. And the closer they are, the smaller these are, right? Cool. Okay, any questions? Okay, so let's go ahead and move on to the next part here. Okay, sorry. So we have Taylor's theorem here. So first of all, f is going to be a differentiable function from Rn to R. Still, we're looking at scalar valued functions. Okay. And let's say we want let's say A here. I'm going to label a point A is a point in Rn. Okay. So the first order Taylor approximation, the formula for the first order Taylor formula is kind of this is how it's phrased. Let me give myself a little more room. We'll bring that back later. Is going to be, again, we're computing points. We're going to take f is going to be some a. F is going to take in some a, right? A point in a, plus some this vector h. Okay, this here is going to be a vector, right? Basically, we're going to say if we have a point and a vector, it's going to move. Basically, we're saying this vector, this h here is going to be something that's small. Okay, this is going to take the place of, right? We can think of if we go back here, the vector h would be h1, h2. Okay, we're going to see that here. Okay, so this is going to be equal to f of a. So just like the linear approximation started with just this a is our like nice point in Rn. Okay, we're going to start by plugging this nice point in, and then we're going to add. This is going to I'm going to use sum notation. So if you're scared of sum notation, I'm sorry, but this is the easiest way to get all of this information down. So the sum is going to go from 1 up to n. Okay. Okay. And now the sum is going to add up hi. So I guess the vector h is equal to h1, h2, all the way up to hn. So hi is just the component, the ith component of this vector. Okay. And then we're going to multiply this by the partial of f with respect to xi. Okay. Evaluated at a. Okay. So this here is basically, if we look up here, is just these two terms here, but it's written in, or I should say these two terms here. It's written using sum notation because up here, the domain was 2-dimensional. Up here, the domain is n-dimensional. And so we'd be spending all day here writing all of the terms if this was not using sum notation. Now in practice, n is going to be, usually we're going to give examples where n is 2 or 3, but it could be as big as we want it to be. But typically we're going to see examples where this is relatively small. Okay, and so far this looks the same as what we had up here, but up here I was always writing approximately, and notice here I'm writing an equal sign, right? And so since this is an approximation, we're going to tack on what I'm going to call the remainder or a leftover term. Okay, and so like a rounding term, maybe, if you want to call it that. I'm using those words because we labeled it with an R. Okay, and so R of this is going to depend on which R1. Actually, I should label it as R1. This is going to depend on A, and this is going to depend on H. Okay, so basically, this is going to be equal to f of A, and then the sum of all of these, what we call first order terms, because we're taking the first derivative of a bunch of f and plugging in a. Okay. And then we're going to add on this error term here. This is kind of an error term. So maybe I'll label that here. So this is like a rounding term, a remainder, or so rounding term or remainder term. I don't like that one as much because remainder makes me think of like division. But error term is probably the best, except that it starts with an R, so it's kind of weird. But or I should say error doesn't start with an R. But this is probably the part that confuses people the most. But the important thing here is basically what Taylor's theorem is doing is it's making this concept of approximation more rigorous, more precise. So in other words, what's happening here is this is saying that this is an equal to, you can put an honest to goodness equal sign here, but you have to take into account this error term. And the nice thing is that R1 of A comma H divided by the norm of H tends to 0 as the norm of H tends to 0. Or you could think of it as, maybe I'll write it this way, as H tends to the point, right, or the vector 0, 0, 0, right, in Rn. Okay, so let's pause for a second before I even get to the second order stuff, okay? So let's pause for a second here. Just take this in because there's a lot to handle here. So the first order term is basically just linear approximation, except it's making it more rigorous. Okay, that's all it's doing. It's taking the idea of linear approximation, which we already saw when we were dealing with tangent planes a couple sections ago, and it's making this idea more rigorous. So what it's saying is, instead of writing an approximation sign, I want to write an honest to goodness equal sign. But in order to do that, I'm going to have to say, okay, if I'm looking near A, so if I take A and I add some vector, basically that's going to give me f of A, which is just what happens at the nice point, plus all of this first order information, which is just the partial derivatives at A scaled down by how far away you are from A. Okay. Again, you can think of this as like a tangent plane. But then this here is going to be your error term. Okay, so I'm going to draw a little picture here to help us out. This is going to be like the n equals 1 picture. So this here is, let's say this is F. Okay. And let's say we have a point on here. This here is the point A. Okay. So this here is f of A. Okay. And now, if we look at the tangent plane, in this case, because n is equal to 1, the tangent plane is actually a tangent line. Okay, we get something like this. Now, if we add on a vector H, so let's say this here is H, then what that does is it moves us to a point over here. This is the actual value of f of A plus H. Okay, green there should be f of A. I'm writing kind of small, so if you're having trouble reading this, please let me know. And I could zoom in later so that you can take a closer look at it. Okay. But you can see that the tangent line here is not giving us a great well, it's not, maybe great is a relative word, but the tangent line would give us this value for A plus H, right? So if I just plugged into this part here, I would get this value here. And so What color haven't I used in this picture? Maybe I'll use that color. Okay. This distance here is exactly my R1. Okay. Now I've flattened this picture so that it's one, so that n is equal to 1. So it's, I guess, it's drawn on the 2D plane, but everything is one dimensional. So it's easier to see, but you could put it up a dimension and you can say, okay, this vector h, it's kind of silly thinking of a one-dimensional vector, but you can think of it instead as a two-dimensional vector. And so then you actually have the graph is some surface living in R3. And so you have this tangent plane at a point, and you're saying if you move away from that point, then there's a little vector downstairs that kind of tells you which way you're pointing. And then upstairs, you can kind of see the distance from the actual graph to the graph of the tangent plane is going to be this R1 here. Okay. Cool. Now, actually, I think I'm probably going to end up doing the second order stuff on a separate slide here. So I'm going to move this down here just because I need a little more space. I want to mention some stuff before I move on. I want to say just that if you read the textbook, so the textbook has explicit formulas for computing R1 of AH. I will say that the textbook doesn't use A here. Sometimes I change the notation that the textbook uses because the textbook likes to use boldface letters. And that's really cool when you're typing, but it's a little harder to communicate when I'm drawing here. So I like to use I like to use slightly different notation to make things more clear. And so just be warned that the textbook does use slightly different notation when it's talking about this stuff. The broad strokes, like the derivatives, the H's, the sum notation, that's all the same. R is the same. But I think the big thing is that like I use A here, but it uses X sub 0 with a bold X. So just be warned about that. I will say regarding this R1, for our sake, I'm never going to ask you to compute R1 because that formula is complicated. And to me, it's not necessarily the point of learning Taylor's theorem. To me, the point of learning Taylor's theorem is learning that you can approximate, basically the idea is that the idea of linear approximation that we were talking about before is mathematically rigorous in this way. Basically, if we're near the point, which is to say that as h gets close to 0, this becomes a better and better approximation. In other words, this here is getting smaller and smaller and smaller. Okay, this here is getting smaller and smaller and smaller here. This term is less and less meaningful the closer we get to, the smaller h gets. In other words, the closer we get to A. Okay, the closer we get to A, the more and more this is just properly what we need. Okay. Okay, so I've got about 5 minutes left. I don't want to bog you down with the second order formula here, but I'm going to just talk about it a little bit. So basically, the first order formula we were saying, okay, how are we going to approximate values of f near A? Well, we just plug in A, and then we have these first order terms, and then we have an error term. Okay. For the second order Taylor's theorem, maybe you remember your first order's Taylor theorem. I think technically, I forget when exactly you learn about that in single variable calculus, but if you remember that, then what we mean by second order is this is going to involve iterated derivatives. So it's going to involve second derivatives. And so up here, we took every possible partial derivative and plugged in A and then multiplied by H. The next one here is going to be, next one is going to involve second order partial derivatives. So second derivatives. And there's more of those, right? And so here we had one term and then n terms, right? 1 plus n terms. Over here, we're going to have 1 plus n plus, and then we're going to have every possible combination of second derivative. So it's going to be more terms. But what that means is now instead of approximating by a plane, we're approximating by what I'm going to call some kind of parabolic shape. So something that actually can have some curves to it. So what that means, if you look at our picture here, is instead of this straight line here, we're going to get something that actually has curves. Maybe it can't follow the blue curve properly, but it's going to follow it slightly better. And so what second order Taylor's theorem is a better approximation of our function f. And so there's still going to be an error term, but you can imagine that error term is going to be smaller. Okay, cool. Okay, so I won't bog you down with too much more stuff. Tomorrow we'll jump right into the second order Taylor's theorem formula, and then we'll see some examples, and then we will we'll get started with 3.3 tomorrow as well. Okay, cool.